Welcome to episode 13. This is the GOBE. It's the Great Ordovician Biodiversification event. If you didn't notice, the last two presentations that I've given use the DK guides as my sort of like template for looking at the covers of, in this case, not magazines, but I've gone back to magazines for this one. In fact, I used Oprah magazine or the O magazine for the inspiration for this one. Of course, that is the Great Basin there in the distance in the background on this. Somewhere, I think it's in the Ochre Range or somewhere, Stansbury Range perhaps, in central Utah, north central Utah. The GOBE stands for the Great Ordovician Biodiversification Event. That's where we're going today. So we have the Cambrian Explosion, which saw this major proliferation of phyla, 20 to 35 different phyla that show up, including the chordates, which we belong to. And it's the first widespread skeletonization of fauna as well. The armor was needed to protect against predation. If we get to the Great Ordovician Biodiversification event, we're really talking just into the Ordovician interval. And so that is probably pretty close to the middle Ordovician, I would say. It saw the filling of many of the niches and the proliferation of many orders. 2 times as many as there were in the Cambrian, and for the families. And so if things were evolving very rapidly, so too were these branches of the trees were just like budding out all over. And so there were 3 times as many families in the Ordovician as there were in the Cambrian. And so it really shows that things happened all of a sudden, and then boom, everything kind of like hits the ground running. You also saw much heavier armoring on many of the animals back then, and so the arms race was really going on strong. By the time we get to the end of the Ordovician, however, it pretty much is the same through the rest of the Paleozoic. And so it takes the very end of the Paleozoic to put the nail in the coffin, says, okay, we're going to start over again, kind of. And so that is going to be the end Permian extinctions. But for right now, we're talking about the Ordovician. And so all of a sudden everything, hey, life is good. Everybody's putting out, lots of different, branches off of their family trees and everything. And it's a long time of relative abundance for these faunas. And so these faunas come along. Some people argue that it's not synchronous everywhere on every continent, but then again, there are different climates affecting each of the different continents as well. And remember, we're not dealing with the supercontinent right now. We're actually dealing with something where all the continents are kind of spread apart. And so it may not be synchronous everywhere. So that's one of the problems that, how do you correlate from one continent to another? Because at this time, in fact, there were many endemic faunas that began to show up. If there were more cosmopolitan faunas during Cambrian time, by the time you get into the Ordovician, every little place had a little slightly different fauna. And they would have different communities of fauna, in fact. And so during the Ordovician, we saw this sort of complex niches that were developing in many of the different sorts of marine settings. We still haven't made that step onto land yet. So these are all marine faunas we're talking about. So what caused the diversity to happen in the first place? Paleogeography has been argued as one of those things. Because you have a widespread sort of set of continents, it would be developing a greater diversity in each one of those continents. There were tectonic events happening at this time as well. The tectonic orogeny was happening off the east coast of the United States. So up around New York and places like that, there was a collision going on during the tectonic orogeny. In fact, it was a little bit offshore from that even. There was an island arc that was approaching and beginning to hit, and that's going to become what we call the tectonic highlands in the northeastern part of the United States. So Maine and New Hampshire and Vermont and that area has that sort of rocks at the very base in that area. There's a lot of volcanic activity. If that was an island arc approaching that was colliding at that time, there was volcanic activity. It was a warm climate for the most part, and so many of the rocks, in fact, were limestones at this time during the lower Ordovician into the middle Ordovician. There was a major sea level fall at the end of the lower Ordovician, and then the beginning of the middle Ordovician saw this sort of like rapid sea level rise again. And so other people have argued, of course, that this has to be related, in fact, to meteorite impacts as well. And so that may be, in fact, and so that's one of the more interesting aspects, and so that's what I'm going to dive into on this presentation. So we're going to look at what were these causes for the Great Ordovician Biodiversification event. I'm not going to get into the fauna as much as I did during the Cambrian, but we're going to talk about some of the events that did occur back then. There were a lot of impacts during Cambrian time, but not nearly as many as there were during Ordovician time. And so I've been to many of these, in fact. So Gardnos is in Norway. Nesbyen is the name of the little town in mid-Norway. So Gardnos is one of the Cambrian impacts. Glover Bluff is in Wisconsin, thought to be Cambrian as well. I've been to Glover Bluff, and it's hard to make sense out of that structure. It's one little monadnock, which is a little isolated remnant. And glaciers removed everything else around it, but there are shatter cones there, so it's got to be an impact of some sort. So it's Glover Bluff. I've never been to Lithuania or Estonia, so I can't tell you about them. And I've never been to Newport, I may have been to Newport, North Dakota, but I've never seen that structure because it's buried in the subsurface. In fact, they produce oil and gas out of it. I have not been to Finland, but I have been to Norway, obviously, and Ritland structure. I've reviewed a couple of papers on that, so Ritland structure is in Norway. AIM structure is in Oklahoma, not too far away from us here in Missouri. But it's actually buried as well and produces oil and gas. Calvin structure is the same story. It produces oil and gas out of an impact structure in southern Michigan. Charlevoix, you've already, I think, seen some photographs of it, but I think maybe I've got one in here anyway. So Charlevoix had shatter cones as well. That's another indicator of an impact event or exposure to shock pressures. So Charlevoix is along the St. Lawrence Seaway, and I got to visit that one in 2018. Clearwater Lakes is up in the northern part of Quebec. Never been there. Decorah, Iowa. It's difficult to understand what's happening at Decorah other than if you look at the core. And I've seen core from Decorah, Iowa, and the Iowa Geological Survey works on that sort of structure. I've been to Granby in Sweden. I've been to Humain in Sweden as well, but I've never really made sense out of the two. I've made it to that area, but never really found the structure itself. Cardlas in Estonia, Lawn Hills in Australia, Lochna. I've attended a couple of different times and visited Lochna and seen some of the structures there. They're really quite astonishing and amazing, actually, structures. When you look at impact structures, you'll notice I keep saying shatter cones. Shatter cones are really kind of cool. I've not seen the shatter cones at Lochna. I don't think that they have any, but they do have some branches that are actually outstanding. It excavated into the seafloor, pounded it so hard, it brought up some Precambrian granites and placed them in the limestones that are around there, some projectile sort of like, it's almost like an eruption in some ways, but it's not an eruption. It's actually something coming from outer space, smacking it and then blasting pieces all over the place. That's what happened in Lochna. Mahlingen, I've not visited, and I've not been to some of the other ones as well here. But so not been to Rock Elm, not been to Pilot, not been to the Slate Islands. Slate Islands are in, I think it's Lake Huron, I think they're in Lake Huron, the north shore of Lake Huron. Tavaren I have been to in Sweden, and it's the deepest part of the Baltic Ocean, the Baltic Sea. And on the east coast, it's a little bit south of Stockholm, and so Tavaren is really amazing. So it's like this, it's a divot, 300-meter deep water in the middle of this lake. It's a saltwater lake. It's in the Baltic, but it's right on the edge of where, dry land over here, 300-meter deep water, and then the Baltic over there, maybe 20 meters deep. So it's like, pretty astonishing. I think it's maybe 200 meters deep. The other thing you get, especially in Scandinavia, at this time interval during the Ordovician, they find fossil meteorites. Now, obviously, meteorites can't be fossils because they were never living, right? But they are fossil in the sense that they are actually preserved in the sedimentary rock succession. So here you can see a meteorite that's embedded in a limestone, and it's discolored the limestone from its original red color. Some limestones are reddish in color, and the minerals have leached out into the surrounding rock there. They've sawed across this thing in order to make a thin section of what it looks like across that meteorite. And there's a coin on there for scale, but it shows you there's a meteorite right there in the middle of a limestone. I've got some more to show you here, actually. So what are fossil meteorites? As of 2017, there had been 115 found. And they're all in Ordovician limestones for the most part. So Ordovician limestone beds are the place where you get these things. Most of them come from one quarry, but it's in Sweden, obviously. There's a whole bunch of Swedish impacts. It's not surprising then to see Swedish places, Swedish quarries would then expose pieces of meteorites that may have been involved with the impacts that actually formed those structures. So this is near the town of Kinnekulla. And so Kinnekulla, if you'll recall, is the name of one of the Lagerstätte, right? So the Lagerstätte is associated with this as well. So the meteorites that they find are elchondrites. So elchondrites have a particular kind of structure in them that makes it easy to identify. And so if you have 95% elchondrite meteorites that you find as fossil meteorites, and they're really rich in chromite, apparently, is the mineral that it's an iron and chromium combination, I guess, in these meteorites. But they also have what they call chondrules. And so chondrules are these little tiny round structures that would have formed in outer space and been a part of that meteorite when it hit the Earth. It still was part of that meteorite. So that's what you get when you're in the asteroid belt. People think that it was in a part of the asteroid belt where it was easy to send many of these chunks or these. They think there was a collision. In fact, if you can imagine, the asteroid belt is in between Mars and Jupiter. And so if you can imagine, at one point, 470 million years ago, kabam, two asteroids strike each other, the debris gets sent out. And if it's in the right place, they get sent towards the Earth. And so that's what they think happened, because most of the meteorites, most of that 115 meteorites, occur through a short time span of about 100,000 years. And so that was about 470 million years ago. So you can tell that they were pretty precise in how they were actually measuring when these things actually hit. So if you can imagine, the same type of meteorites keep striking the Earth, keep getting incorporated as fossil meteorites into the limestones at Kinnekulla. And so it rained meteorites on Earth for a long period of time. So what has that got to do with biodiversification? Meteorites, when they strike the Earth, can send up clouds of material. And so some people think that it could have caused cooling. And so 470 million years ago, if it began to cool, that can actually force evolution to occur quite rapidly, is what people think. People think that's why humans evolved fairly rapidly over the last ice age. Here's that quarry, the Thorsberg quarry in Sweden. Here you can actually see where they're excavating the rocks out layer by layer, very carefully removing the layers. Here you can see another one of these fossil meteorites. A smaller area had been affected by the leaching of the minerals out of that meteorite here. And on the left-hand side over here, you can actually see a cube. Well, very commonly when you find a meteorite, you will find that they put a cube in there that indicates the size. That's 1 centimeter wide cube. It's like a little die that they put there to identify it. In fact, that's from the Thorsberg fossil meteorite here. And so that's what you see in the cube over here. At the bottom of this image is an orthocerid cephalopod. It's a straight cephalopod that dates back to the Ordovician, and so you can actually see the layers of infilling of that cephalopod. So, fossil meteorite here. Really pretty cool. Here's one up close here. This one's nice because you can actually see the chondrules in it. If you look right in the center of this, you can actually see 5 little chondrules. Most of them are roundish. One of them's a little bit more squarish or rectangular, but those are what the chondrules look like. If you were to just to look at an L chondrite meteorite, it would look something like this. And so you can see the round features in this meteorite as well. Now, this is not a fossil meteorite. This is just an L chondrite, just to show you. But they're very common on Earth, as it turns out. They're one of the more common meteorites that you would find, in fact. And so I think 90% of the meteorites that strike the Earth are L chondrites, but many of them happened over this very short time interval during the Ordovician. So that's one of the leading hypotheses about not only do you get a lot of impacts, maybe throwing a lot of like disruption in the environment, but also maybe dust clouds into the air and so forth. They're all the same variety of meteorites. And so, wow, that's cool. Here's that shatter cone from Charlevoix. So Charlevoix is one of the places where you had an impact. Now, this was not actually, it was solid rock when this thing hit, but it is an Ordovician limestone. And so, boom, here's these features that go through that rock. It's one of the few things other than a fossil meteorite that you can look at and say, that came from a meteorite. That came from the blast of the meteorite anyway. And so that is an area, if you can imagine, when you have a meteorite strike the Earth, what it does, it sends out shock waves all over the place, and those shock waves can actually interfere with one another. And so when they cross one another, you can form these sort of features that are called shatter cones. So that is a shatter cone right here from Charlevoix. And it's right along the St. Lawrence Seaway in Quebec. This is also in Quebec. It shows you some of the Cambrian age rock. Actually, these are Ordovician age rocks right here, but a series of shales and limestones that were deposited. I got to visit this area in 2018, go on a nice deep water sedimentation sort of record for the Ordovician here. There are some Cambrian age rocks around here. They didn't know. They thought that these were actually Ordovician. These were Cambrian in age. And I picked up a rock and said, no, these are graptolites in here. This has to be Ordovician. Because the earliest graptolites were actually dendroid graptolites that were the only variety that were around in the Cambrian. By the time you got to the Ordovician, that's when you first got the regular graptolites, and that's what these things were. And so, look, here's the graptolites right here. This has to be Ordovician in age. And so that's what you see in deep water sedimentation here. Whole series of layers of rock that would have represented deep water sediment, gravity flow sorts of deposits off of a shelf. This is the same sort of succession, but it's not as beautifully exposed in a cliff along the shore there. This is more along the actual beach itself. You can actually see some of the rocks that were down here at the end, however, and those rocks are it was pretty cool to see them. That's one of the nice things about being a geologist. You get to travel to some kind of relatively exotic places. So Quebec was right up there for me. I enjoy going to Europe. And if you want to go to Europe and not spend the money to go on an overseas flight, you can go to Quebec. It's just like going to France. It's more French than France, probably. So that's Quebec. Here's the reconstruction for what it would have looked like during the Cambrian. Remember, at the end of the late Proterozoic, we had a breakup of that supercontinent that we called Rodinia. So Gondwana was still together at that time, but the rest of these pieces, Siberia, Baltica, Kazakhstan, and Laurentia had broken apart, and even the South American part of Gondwana, that should be attached to Gondwana on the other side over here, across through the South Pole there. Australia, they show attached to Gondwana as well, and Gondwana also included Antarctica at that time. So all of Eurasia was part of Gondwana too, except for Kazakhstan and Siberia, obviously here, and the Baltic region. But much of Asia was around back then. And so here you can actually see China's breaking apart from the rest of Gondwana here. This is what's happening during the Ordovician. So this comes from Encyclopedia Britannica and the image before this. So I've used these images to avoid, any problems with the PaleoMap project. There's a whole bunch of different reconstructions, but these seem to be fairly consistent with, what most people think is going on at this time. Laurentia is essentially floating separate from the rest of these continents, the smaller continents at that time. So here you can see Siberia kind of getting closer to North America, Baltica getting closer. And if you look at Laurentia here, you can actually see offshore there. That's the beginning of the Taconic Islands down here. So Taconic orogeny is going to happen from that small island arc beginning to hit Laurentia down here. By the time we get into Silurian time, and we're not going to spend a whole lot of time in Silurian, but Baltica is slamming into Laurentia at that time, and we're gonna have the beginnings of yet another orogeny at that time called the Akkadian orogeny. The Akkadian orogeny is going to in fact go on into the Devonian, and it's primarily Devonian in age, in fact. So that's when you get Baltica and most of the British Isles attached to Baltica at that time, colliding with North America. And so at this time, it's called the Avalon terrain that's docking with us, not the Taconic terrain. Taconic terrain's already collided and left behind its calling card in New England area of the U.S. Here, by the time we get into Devonian time, you can see that everything's crunching together during Devonian time. So Baltica and Siberia and Laurussia, there's actually a piece of Laurussia that is attached to Laurentia as well here. So we're forming mountains at this time, but we have an ancient ocean that will disappear at some point in the Paleotethys down here. And China's floating free here, and the rest of Gondwana is down here at the polar regions, and that's going to be a source for glaciation later in Ordovician time, in fact. And so in North Africa, there is evidence for glaciation during Ordovician time. North Africa. By the time you get to Devonian time, there's going to be more evidence for glaciation as well. So, the late Ordovician climate change. So we have this evolution going on at this time. People argue about what caused it, right? We already know that there are impacts at that time. There's also a major climate change beginning to form. After having a nice, into the Cambrian, fairly warm for most of it, maybe a couple of episodes of cold snaps, if you will. Cold snaps meaning maybe 1 million or 2 years of cold weather, and all of a sudden, by the time you get to the late Ordovician, things change. So we have a way to figure this out. How do we know the climate changed during the Ordovician? Well, we have limestones, right? So we have the limestones, and the limestones are made out of calcium carbonate, right? Well, carbonate is CO3. And as it turns out, carbon and oxygen are really good for determining paleoclimates. We can get at an isotope of carbon called carbon-13. Normally, carbon has a mass of 12. And carbon-14 doesn't last very long, other than 50,000 years, and it disappears into nitrogen, essentially, because of its absolute age dating. It's only good back to about 50,000 years. And it just disintegrates or degrades into nitrogen. So for carbon-13, that's a stable isotope, however. And so if you compare the amount of carbon-13 with the amount of carbon-12 in the carbonate fraction, in the carbonate rocks, it gives you an indication of what the ocean productivity is like. And so carbon-13 excursions are thought to reflect ocean productivity. So if you have a negative excursion of carbon-13, delta 13C, we called it, it's the comparison of 13 to 12. If that ratio decreases, that means that it was probably a colder climate. And so that's carbon-13 excursion that you would get. That's what you see in this diagram right here, in fact. You have this pulse of glaciation, in fact, recorded. We have a physical evidence for that in the form of glacial diamictites in North Africa. When it comes to oxygen isotopes, now that's a slightly different story. Oxygen isotopes also record climate change, but not primary productivity. If you have cold oceans, you're going to have less productivity. There's going to be fewer phytoplankton that are out in the oceans. Therefore, it's going to be kind of tougher on the animals, I guess you could say. We're talking about the close of the Ordovician now. The great biodiversification's already occurred, but something's going to happen now. And this is going to lead to one of the first mass extinctions on Earth that we know of, to the metazoans anyway. So during when you're capturing when you're capturing carbonate ion, let's say CaCO3, your carbonate is there in the limestone. And when you take it into a mass spectrometer, you can compare the amount of oxygen 18 to oxygen 16, as it turns out. 18 is an isotope. It's a stable isotope of oxygen. 16 is the more common variety of oxygen. It's the kind that we breathe most of the time. But if you compare 18 to 16, it's called delta 18O when we make that comparison, differential between 18 and 16. If you have shifts in that, now if you can imagine this, in the oceans, when you have water evaporate out of the oceans, it's preferentially going to take the light isotopes with it in order to take them to a place where they can then be precipitated out as ice and snow in polar regions, let's say. And the poles at that time were in Africa, North Africa, in fact. And so you take out the light oxygen, so it's going to enrich the oceans in delta 18O. The 18O is going to go up in value. And so people make comparisons through these rocks. And so delta 18O is going to give you an indication of glaciation as well, or climate change anyway. And so between comparing the ocean productivity and the glaciations that may occur with delta 18O, and that changes with latitude as well. So there's a latitudinal effect as well. Anyway, it indicates that there was global cooling going on through this entire interval from the lower Ordovician. It begins to cool, and then it really begins to cool in the upper Ordovician. And it cooled so much that we went through in a time called the Hernantian. In the Hernantian, there's actually a glaciation that occurred at that time. The mass extinction occurs right then as well. So right just before you get to the Silurian mass extinction, it's called the terminal Ordovician mass extinction. So we're going to talk about extinctions a lot in the remainder of the 2 weeks that we have left here. So extinctions are pretty important in the history of life. We like to say that there are 5. There are 5 of them altogether. They call them the Big 5, in fact. The first one is the late Ordovician extinctions. Most people agree that it's probably related to climate change. Probably. The next major one is in the Devonian, and that's the next chapter along the way here. So yeah, welcome to the end of the Ordovician, and yeah, we're going to have an extinction. Sorry. So anyway, that's the end of the Great Ordovician Biodiversity event. Even though things stay very diverse for the rest of the Paleozoic, that major pulse of diversification, that's over at the end of the Devonian. All of a sudden, it does stay the same. It stays high. Diversity stays high because you've already got that tree that's spread out, and the tree of life, essentially. So it expanded from the Cambrian into the Ordovician, and then it stays the same kind of after that. We're never going to see the same sort of blooming again after the Ordovician extinctions. Yeah, we get some recovery, obviously, because we're here today, right? So our ancestors made it through that, whatever fish those were. So here we are today. Okay, well, we're going to leave it at that. This will be a little bit shorter than the other ones, but, it's worth doing shorter ones every once in a while. I'm trying to get these done. I'm trying to get them uploaded for you. So anyway, sorry for... Yeah, you wouldn't believe. Okay, so anyway, this is the first time I've taught this. This is the first block class I've taught, I think, ever at the university. So, but anyway, we'll get this thing done as best we can. And so this is the third one that I've recorded today. Maybe I'll get one more. Who knows? Thanks for your time. Thanks for your attention. And I think there's some important stuff here, so study this. We're supposed to have a quiz over these last 3 presentations on Tuesday. So you'll have the presentations up. You already have the presentations online. So anyway, talk to you soon. Thanks now. Yeah, bye.